In this video, we're going to find the electric field at the center of a uniformly charged half ring by using a physical integral. So in the problem, we're told that the ring has a total charge of Q and a radius of R, and that charge is distributed uniformly across the ring. And we can already see by symmetry that the electric field must point along the symmetry axis of the half ring. We can justify this fact by saying that the ring has mirror symmetry across that axis. Or in other words, there's no way to bias the electric field upward or downward when the ring has exactly the same charge distribution above and below that symmetry axis. And our basic strategy for the problem is to break the ring into little point charge increments that we call dQs. Each dQ will contribute an increment of electric field pointing radially away from that charge. And that contribution to the total electric field, we're going to call that dE. Now we already know that the horizontal component of dE is the only part that matters because every dQ that lies above the symmetry axis is matched by another dQ below the symmetry axis, and this causes the vertical components of electric field to cancel each other out. So we're just keeping that horizontal component dE sub x. And with our charge located at an angle of theta above the horizontal, we can see that we also get this angle of theta between dE and its horizontal component. And this means we can get that horizontal component, dE sub x, by taking dE multiplied by the cosine of theta. Now, before we finish setting up this integral, we need a quick note on linear charge density. The linear charge density is the charge per unit length along this ring. We would measure that in coulombs per meter, and we normally give this the symbol lambda. And it's not hard to calculate that linear charge density. It's given by the total charge on the ring, that's Q, divided by the length of the ring, which is pi times r. That's half the circumference of a circle because we're just looking at half of a circle here. We can also turn this around to say that the total charge on the half ring is given by lambda multiplied by pi r. And we're going to use that expression toward the end of this problem. So notice what we're looking at there is charge per unit length multiplied by length. That gives us the total charge. And this idea of linear charge density multiplied by length can also be applied to dQ itself. And we can say that dQ is lambda times ds, where ds is a small increment of arc along the ring. Finally, ds can be written in terms of theta by using our old formula for arc length, s equals r theta. Our little segment of arc takes up a differential angle of d theta, so we can say that ds is r d theta. This allows us to write dQ as lambda r d theta. At this point, we're ready to use the formula for the electric field produced by a point charge in order to find the contribution to the total electric field given by this little dQ. So that incremental contribution to the electric field, we call that dE, is given by the usual point charge formula. We get the charge in the numerator, dQ, over 4 pi epsilon 0 times r squared. And r there is just the distance between the charge and the observation point where we're measuring the electric field. Now we can replace the dQ with our expression in terms of linear charge density. So dQ has been replaced with lambda times r d theta, and we still have that denominator of 4 pi epsilon 0 r squared. Now remember, what we really want to add up here is all the x component contributions. So we really want an expression for dE sub x, and all we have to do there is tack on that cosine of theta. And we'll go ahead and cancel one factor of r at this point. And now dE sub x is entirely phrased in terms of this angle theta and the differential d theta. Everything else there is a constant, so we're ready to integrate. To get the total x electric field, which gives us the magnitude of the total electric field itself, we're just going to sum up all of the dEx's. And this is what an integral does. It's a summation device for a bunch of continuously changing infinitesimal contributions. So we just plug in our expression for dx, and I'm going to move the constants out in front of the integral while we do this. So there's a lambda over 4 pi epsilon 0 r out in front. And then we have the integral of cosine theta d theta. This is a theta integral, and we have to think, what are the bounds on theta the way it was defined so that we cover the entire ring? And the way we defined theta was, we're thinking of it as 0 if it lies on the symmetry axis. We were measuring it positively as we rotated clockwise off the symmetry axis. So to get all the way to the bottom of the ring, that's a theta of negative pi over 2. And to get to the top of the ring, that's a theta of positive pi over 2. So there's our limits of integration, negative pi over 2 to pi over 2. Now we just guess the antiderivative, and that's the sine of theta. So we have lambda over 4 pi epsilon 0 r times the sine of theta evaluated as theta goes from negative pi over 2 to positive pi over 2. Now when we plug in that upper limit, we get the sine of pi over 2, which is 1. And then we subtract what we get when we plug in the lower limit, the sine of negative pi over 2, which is negative 1. So this gives us 1 minus negative 1, or 2 in those parentheses. I'll go ahead and cancel that with one of the 2's in the denominator. This leaves us with lambda over 2 pi epsilon 0 r. Now that's a fine way to leave the answer, but if you notice in the instructions for the problem, we were asked to express the final answer in terms of the total charge Q. And the way we can get this done is remembering that we have this expression relating the linear charge density to the total charge on the half ring. Lambda times pi r is actually Q. So what I'm going to do is multiply the top and bottom of this expression by pi times r. Now the numerator is just the total charge Q, and the denominator, that's 2 pi squared epsilon 0 r squared. And we're done. If you enjoyed this video or at least found it useful, check out another one by clicking one of the links on the left, or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.